Welcome students. In today's class, we are going to study about the electrical properties and magnetic properties of the solids. The electrical properties, based on the electrical properties, whether they can conduct the electricity or no, whether they can conduct the heat or no, depending on that, the substances are divided into three types: metal, non-metal and metalloids. Metals are good conductor of heat and electricity, whereas non-metals are the poor conductor of heat and electricity. When it comes to your metalloids, they are also the poor conductor of heat and electricity. The properties of these things, whether it is a good conductor or a poor conductor or the bad conductor, can be explained with the help of band theory. According to the band theory, every substance or a metal is having the inner shell and an valence shell. The valence shell is always at the higher energy level. These valence shell or the valence band contains the electron, which are valence shell electrons. In the PO first, you have already studied what you mean by the valence shell electrons. The electrons which are present at the valence shell orbital are known as the valence shell electron or valence electrons. In some of the metals, at room temperature, some of the valence electron can leave the valence band and go to higher energy level. And these electrons are called as free electrons. These free electrons are responsible for the current in the conductors. Hence, these electrons are also known as conduction electrons. And the band where these electrons are present is known as conduction band. This conduction band can be either empty or can be partially filled. And the gap between these valence shell and the conduction band is known as forbidden energy gap. And for an electron to transfer from valence band to conduction band, the external energy whatever you are going to supply, it should be equal to forbidden energy gap. Then only the electrons of the valence band can jump from valence band to conduction band. Depending on the gap, that is forbidden energy gap, there are three types of these solids, and the solids three types can be conductor, insulator or semiconductors. Let us see, according to band theory, how these conductors, semiconductors and insulators are explained. When the gap between the conduction band and valence band is 0, that means there is no gap. Second possibility is the gap between the valence band and the conduction band is very, very high. Whereas third possibility is it is in between 0 and high, that is the energy gap is small. If the gap is 0, the forbidden energy is very, very less. Hence, easily the electrons from valence shell can go to the conduction band and they can conduct the electricity and the heat, and they are known as conductors. When the gap between the valence band and the conduction band is very high, the electron jump cannot take place. Hence, they cannot easily conduct the electricity. Hence, they are called as insulator. Whereas, the third type, which is in between the conductor and insulator, is known as semiconductors. Let me start with the conductors. The energy difference between the partially or completely filled valence band and empty conduction band is negligible, or also we can say as it is almost 0. Hence, the electron flow will take place very easily. How it will be? See, the valence band and the conduction band, they are almost attached to each other. Hence, the electrons from valence band can easily go to the conduction. Hence, they will easily conduct the electricity and heat, and they are known as conductors. The second case, the gap between the valence band and the conduction band is very high. When the gap between the very high, the transfer of electron will be difficult from valence band to the conduction band, and they act as bad conductor of heat and electricity, and they are known as insulators. Example for the insulators are glass, rubber, plastic, wool, etc. The third type, which is an very important, that is nothing but your semiconductors. The gap between the valence band and conduction band is comparable small. It is not too large, too small, it is comparatively small. Hence, the electron will easily jump from valence shell to the conduction shell or conduction band. Hence, some of the electrons will jump from valence band, and this type of semiconductors is known as intrinsic semiconductors. Examples are silicon, germanium, etc. However, we can increase the conduction by adding the impurities like arsenic and boron. And this process of adding the impurity to the pure metal lattice is known as doping. And the result of this one, semiconductors are called as extrinsic semiconductors. And how these impurities are going to be added, and what are those are called as? They are called as dopants. Let me take one type of this semiconductor, that is extrinsic semiconductor, that is N-type semiconductors. Let us consider one silicon lattice in which the silicon is having the atomic number 14, and the electronic configuration of silicon is 1s2, 2s2, 2p6, 3s2, 3p2. Calculate the valence shell electrons. 2 plus 2 equal to 4. So, I am having 4 valence electron across each silicon, and it is shared with 4 neighboring silicons like this. They are shared between 4 silicon. The center silicon I have considered. If we doping with group 15, that is arsenic. If you are doping with the group 15, that is arsenic. Arsenic atomic number is 33, and it contains totally 5 valence shell electrons. Now, I replace the silicon with arsenic, and 5 electrons I have placed with the red color. Now, you can see one extra electron is there, which is an free electron. So, what will happen? The 5th electron, which is free, and it will be delocalized. It is going to move in any direction, and due to this delocalization of the free electron, it will increase the conductivity. Hence, they are called as N-type semiconductors. N stands for negative. Then electron is having the negative charge, and you can remember negative type of semiconductor is due to the electrons. Whereas second type is p-type semiconductors. As I said, p means positive. Let us consider the silicon lattice. The same atomic number of the silicon is 14, and valence shell contain the total 4 electrons which are shared between the 4 neighboring silicon atoms. Now, the doping is done with the boron family member. When the doping is done with the boron family, whose atomic number is 5 and valence electrons are 3. Already we are having the 4, but now boron is going to give only 3. So, we are going to left with one vacant place, that is going to act as an hole. At one place there is no electron and their vacancy, or it will become a hole. This hole should be neutralized. Now, to form the covalent bond between this boron and silicon, boron, what it will do? It will take an electron from the neighboring silicon atoms. It will not take from 1, 2, 3, 4. It will take either here or here or here or here, because already boron has formed the covalent bond between these 3 and it is going to form a bond between this. So, the electron should be taken from here. So, the now covalent bond is formed by borrowing the electron from the neighboring silicon atom. The electron has came from here and the new covalent bond is formed, and which leads into formation of hole with respect to this silicon atom. Now, this silicon atom which is having the hole, it should be neutralized, or it should form a covalent bond between these two. Hence, the one of the electron from here it will jump here, or here it is going to be jump, which is not shared between these two. Similarly, one more hole has been formed and it is neutralized by this silicon. The process it will be continued now, and this leads into the conduction, and this conduction is mainly due to the hole. That means, electrons which are going to occupy the hole, which are responsible for the conduction. Hence, these holes are considered to be positively charged. It is known as p-type semiconductors. Now, the difference between the n-type and p-type semiconductors. In the n-type semiconductors, they are doped by pentavalent atoms, that is belonging to group 15, whereas in p-type semiconductors, they are doped with trivalent atoms, that is group 13 elements, or we can say as boron family. And in n-type semiconductors, electrons will be contributing to the conduction, whereas in p-type, the holes are contributing to the conduction. Let us move to the second part, magnetic properties of the substances. The magnetic properties of the substances, you know already, electrons will revolve around the nucleus in various orbits. Also, they are spinning along with their own axis. When the electrons are revolving around the central nucleus and along with their own axis, due to the spinning, the magnetic field is going to be generated. The electron is spinning around itself and also it is spinning around the nucleus, and hence spinning of electrons acts like an tiny magnet or a small magnet. In the last year you have already studied in the structure of atoms, wherever we are having the 1s orbital, n is equal to 1, L is equal to 0 and magnetic quantum number is equal to 0. 2px, 2py and 2pz, there n is equal to 2 and L azimuthal quantum number is equal to 1. Hence, the magnetic quantum number is going to range from -1 to +1, -1, 0 and +1. And these are called as arbitrary assignment. If the electron contains 2 electrons, then one electron spins in the clockwise direction and the second one spins in the anti-clockwise direction, due to which the spins are going to be balanced. When the spins are completely balanced, they will become neutral and magnetic property will not be observed. If an orbital contains only one electron, then the spin will be either in the clockwise or anti-clockwise direction. This unbalanced spin is going to exhibit the magnetism. See here, one electron is moving from anti-clockwise and one is clockwise, anti-clockwise direction. And due to this, we are going to expect either plus half or minus half as the values. And these values will result in 3 types of the magnetic properties, mainly for your syllabus. First one is diamagnetism. Diamagnetic substances are weakly repelled by the magnetic field. If the same substance is kept under the influence of the magnetic field, these substances will be weakly repelled and they are known as diamagnetic, and they do not contain any unpaired electron. That means we are having even number of the electrons in the same orbital. That means they will become balanced, that is spin will be balanced. Examples for the diamagnetic substances are water, sodium chloride, benzene. Very, very important definition. The substances which are weakly repelled by the magnetic field are known as diamagnetic substances. And example. Second one is paramagnetism. The substances which are weakly attracted by the magnetic field are known as paramagnetic substances. Now you can imagine the diamagnetic was due to absence of the unpaired electron, but here it should be present. So paramagnetism is due to the presence of one or more unpaired electron which are attracted by the magnetic field. As the number of unpaired electron increases, magnetic property will also increase. Example, oxygen, copper plus 2, ferric, chromium plus 3 oxidation states. Third one, ferromagnetism. Substances which are strongly attracted by the magnetic field are called as ferromagnetic substances. Or in some of the books you can also see that ferromagnetic substance which possess the permanent magnetic field. They will also define like that. So example for that is iron, cobalt, nickel, gadolinium and chromium oxide. Here you can remember this one with the help alnico, AlNiCO, Al aluminium, Co cobalt, Ni nickel, alnico. The fourth one is antiferromagnetism, which is not so important, but you have to remember. In the beginning itself I told there are mainly 3 types of the properties you have to remember, that is diamagnetic, paramagnetic and ferromagnetic. The fourth one is antiferromagnetic. The substances which have unpaired electron and also domains like ferromagnetic substances, but they are not attracted by the magnetic field. That means they are having the unpaired electrons. They should act like a ferromagnetic substances, but they are not going to act as a ferromagnetic substance. That means they are not attracted by the magnetic field and they are known as antiferromagnetic substances. Example is MnO, manganese oxide. And ferrimagnetism, substances which have unpaired electron and also domains like ferromagnetic substances, but weakly attracted. Ferromagnetic substances are strongly attracted, but here we are having the unpaired electron, they should act as a ferromagnetic, but they are weakly attracted. That means they are going to show the property of the paramagnetism, whereas antiferromagnetism is showing the property of the diamagnetic. So, these types of substances which are weakly attracted by the magnetic field, even though they should act as a ferromagnetic, are known as ferrimagnetic substances. And the examples are magnetites and ferrites. Thank you.